Okay. Share. Okay, so this one is a model that translates text and speech from one language to another language. This is a difficult problem. Okay. Do you think this is possible to translate from one language to another? Yeah, it's a solved problem, actually. Right? So astonishingly, this can be done really well today. So yeah, so how do we think about this one? A model that translates from one language to another language. So yeah.
So you're dealing with both text and speech.
And just to make it more complicated, yeah, I made it text and speech.
Oh, okay.
That's right.
So it's also text and audio input.
Yes.
Oh.
Exactly right. That's the point, yeah. To torture the students. All right, so let's go to the whiteboard, okay? And I'm gonna create a new one. So I should be recording, I think. I think that means it's recording. Yeah. All right, let's do a new screen. Okay, so again, where do you start? Do you just say, let's apply RNNs or no, right? Or CNNs? No. Think through the problem, read papers, and then, yeah, start, trying to find solutions. So let's kind of visualize this. We want to translate a sentence from one language, let's say Japanese, to another language, let's say English. Right? What do we have in this? We're going to have several words, right? Just going to use like 5 words. Now, are we guaranteed that we're going to have 5 words on the other side? Like if the Japanese sentence has 5 words? No. We could, 5 words in Japanese could be, I don't know, more words in English. Do you see that? That already makes it very difficult because it's not, a vector of a specific size to a vector of another specific size, right? Now, there's a solution to this already. This is how ChatGPT works and solves a lot of problems. We're not going to talk about how transformers work and how it does it. We're just going to very simply think about it with what we know in our second week of machine learning. Do you guys see that? All right. So we want to think about this. Now, the output is what? A sentence, right? It's not a class anymore, right? And it's not a regression value either. What is it instead? It is a set of tokens. That's what words are referred to here. And the input is another set of tokens. Now the question is which tokens? What is this tokens? So the first thing you do in these kinds of problems is you define a vocabulary. It's like the vocabulary that you're going to use for this. Do you guys see that? So now, okay, what is that vocabulary? Well, you have to think about it. What are the words that you're going to use, right? To translate from one to the other. And so you need, basically an English vocabulary and a Japanese vocabulary. And then you define the size of it. Now, how many words would you say is enough for a language? How many? Well, but how many? Let's just, we always want to give.
For day-to-day speech, 3,000 English words will be enough.
3,000 English words?
Yeah.
It might be very limited.
Yeah, day-to-day speech. But
yeah.
If you need, then it will be, if you talk about high literature, all the papers, that's probably 10,000.
Yeah, 10,000. Okay, so let's say 50,000 actually. Okay. So I'm going to say 50,000 and 50,000, 50K, right? 50K. Those are the tokens. Do you guys follow this? Okay. How do you know which 50,000 to select? Select the most frequent ones. You see that? So xylophone is probably not a word you want to include, right? But include something that's food, those kinds of things. Got it? Everyone with me? All right. And then what do? this vocabulary goes from 1 to 50,000, right? And you can't give words or letters to machine learning. Machine learning algorithms cannot deal with text. All they understand is numbers, right? So you have to give it numbers. So what you do is you basically, each token will have an ID, which is a number. So like word 49,000 will be maybe bird. But we're going to represent the word bird with 49,000. Do you see that? And it becomes a number. Everyone with me? So then effectively what happens to a sentence in Japanese and a sentence in English, so let's say English and Japanese, is that a sentence is no longer made up of the words themselves, but what? The ID that corresponds to that. So it might be like, yeah, 17, 5,000, 3, 44. You see that? That's what it is. And then on this side, it's going to be the equivalent, 25, 1, 43,000, yeah, 43,000, 15,000, and so on. Got it? And now we're starting to convert this thing into numbers, right? And now at least we have a way of correlating this to that because we've converted it to numbers. Do you see that? So, okay. So now that I've described, now I haven't even brought in speech in here. Okay, so speech is another thing that we can add on later. How do we do that? We just concatenate another vector, right? That's it. So like if I had a vector of the words, I can just concatenate another vector and make it longer, right? And one key thing that we're going to do to make things simple is that we make these vectors of a constant size. So we make it like a buffer size. So what does that mean? It means that a sentence can be how long? How long is a sentence in general? 5 to 7 words. So how about we just make 10 words the constant here? So if we have a sentence that is less than 10 words, what do? We just put zeros at the end. We pad it like spaces. And if, unfortunately, if we have a sentence that's longer than 10, we like truncate it. So we lose a little bit of information, but it's going to be a rare case because we picked a value that's enough for most. Got it? You see that? So you have to make all these assumptions, again, with the goal of arriving at what? Dimensions for our vectors. Fixed dimensions for our vectors. I mean, the transformers work very much like this. So they have a limit right now of more than 756 words. So they can, they're that big. Because it really all depends on the amount of memory, GPU, so they can make them pretty big. And that usually holds everything. Got it? All right. So, and there's other tricks, but right now I'm only using words. They actually use something more equivalent to syllables so that they can construct new words that haven't been seen before. But let's just keep it at words. So we said that this is of size 10, number of tokens. And then this is the speech equivalent. So remember that speech is going to be what? What does speech look like? It looks like a whole bunch of, waves, right? A dot wave file, WAV, right? So the only thing we need to do is whenever somebody says something and we've got the text, like the transcript, we also record the wave file over that period of time. Got it, guys? And so if I have the 10 words for that sentence, then I need to have over here on this side, what? The equivalent sound segment, right? You guys see that? And then there's a lot of techniques that one can use to just extract things like the pitch, right? There's something called formants, and several other, there's like basic algorithms that you can use to just extract certain pieces of information about the signal. For now, we're just going to kind of assume, let's say, for the sake of argument, that we have a sentence and then we have a wave file, and for every single one, we're going to extract 10 things of that wave file again. So that could be, as I said, pitch, timbre, all kinds of things like that. All right. And so that's going to be then size 10, which is information about the speech signal. Got it? That's important because if you speak, right, and you say a sentence, you have a certain pitch, and then if you speak and you say something, the same thing actually, but you have a slightly different pitch, right? And so also the emotion, the way that you're saying things, you might be very excited or, and so all of that can be captured here. The goal is to translate better somehow, okay? Everyone with me? So again, this is a huge, complicated problem, right? And so we're only trying to think of it in terms of answering the questions that I asked you. What is a sample? What is X? What is Y? And so on. Got it? All right. So now that we've defined all of this, let's, once again, if we start getting lost, X and Y. Now, the X, I drew it a certain way. What about the Y? I can already intuitively say that Y should be of probably the same size as X, right? Because in a sense, we agreed that they're like fixed size, right? To account for the fact that some may be shorter than others. And we're going to do padding or truncating. So, okay, X and Y, inputs and outputs. Samples, they should be the same. So how many? So let's start. That should be easy, right? How many samples would we have? We're trying to translate from English to Japanese. We need a lot for that.
Millions.
Yeah, millions. So I once looked at translating English to Spanish, and I grabbed the European Parliament. When they do the Parliament, they have to do it in all the languages of Europe, right? And so that's a nice data set because you can grab one language and another one. And I did 2 million pairs of sentences. So the English to Spanish or English to French. So that's a lot. 2 million provided good results. I can say that for sure. Actually, very good results. So
Probably 20 million for Japanese.
is it?
Yeah, it's because the other language pairs are very similar.
That's true. That's true.
Yeah.
And this might be very different, right? And I don't know where you would get a data set, but I'm sure there's a data set somewhere. So good. So 2 million. So the point with this, it's not so much the details. The point of this one is what? To understand that you need a lot, 2 million, for this system to be effective. Got it, guys? Question? Yeah, please go ahead. That's a good one, right? So you're making a good point. What did I say in the problem? So we use what? It just depends on what I said on the
text and speech. So the way you did it should output text and speech as well.
I may have asked for that. So it's whatever, how do I share? Okay, so a model that translates text and speech from one language to another language. So really, we want, if we hear Japanese audio and see the text, we want English audio and text. Okay, yeah. Oh yeah, sure. So I just want to say generative models do this, right? The whole generative neural networks are doing this. They're generating images, they generate audio. You can literally nowadays, I think they were trying to get an unfinished song by the Beatles because Elton John passed away and he didn't finish part of it, I think. So they created a model that sounded like him to kind of complete that song. So it's possible. It's very complex, but it's possible. All right, sorry, to answer your question. You can look that up. I'm pretty sure that's true. All right, go back to the whiteboard. Yes, what's your question?
So here, we are finding it's a key value pair for the text, 25 and 70 for the text thing. But for the audio file, are we going to get like a Japanese audio file which says, for example, food, and the English audio file which says food, I don't know.
Yeah, no, I think I understand what you're saying. So I said that So let's just think of this one as a row, right? Let's take sample one. So we know that one, and so I keep forgetting, this is English. This is English. So this is Japanese. Let me just, so we know. What was this? All right, so. Yeah, your question is pretty good. So this is Japanese, correct? Yeah. All right, Japanese. And then this is English. So we know we've got the first row is a sample, right? One, the Japanese text plus the 20 or 10 features that we extracted from the audio, right? And then what we want to do is on this other side, we want to produce English text, and it would have, if we're using this methodology, then we would produce these 10 as well. Yeah, and so these, well, I think your question is that these 10 are not audio. They're extracted from audio. So then, yes, what we would have to do is take these 10 and reconstruct the audio from them. So it's gotta be that. Yeah, that's a good point. I mean, and if we can take an audio file, make it into 10 features, and then from those 10 features, go back to the audio. Okay, so remember, this is a simple example, so I'm not giving you the solution to this, but it's a good question. Yes.
So
Yes,
you-
yes, yeah.
Oh, so you concatenated the two into one.
One
string-
vector.
Yeah, one vector.
One vector, yes.
So you get another vector out, then do you have to break them apart in order to?
They have to be constant, yes. So that's why I said it's almost like you have to picture it like this.
Cut it, yeah, and then,
And they have to be, this is a thing because you're doing a lot of matrix multiplications and things like that. So that it has to be set in stone and it can't like move. And so that the things can move inside, right? Like the sentence could be pretty short or pretty long, but it's always restricted to living here.
Right.
And then the audio would be the same. So this audio actually, since we said extract 10, it would have to be 10 that would allow you to reconstruct. If not, then it, we had a bigger challenge. Lucas.
If the Y output is just text. Could it be?
Text or speech, but yeah.
Uh,
Oh, you want it just to be text, yeah.
Yeah, say if it was just text, could maybe also like look for tone based on the audio, like the English translation.
Okay, so you're saying not basically reproducing your voice, but just the tone that you had.
Yeah.
Yeah, and that's like a synthesizer, right? So you take the text and you synthesize it kind of towards your timbre or your characteristics of your voice. All of this definitely can be done. Yeah. It's a very good question. Do you guys understand me? My interest is that you understand the correlation, right? And the beauty, and this is hopefully something that you will start to pick up with machine learning, is that you don't always with machine learning have to figure out everything. That's the beauty of it. You let the machine learning algorithm figure it out for itself. That's why you give it 2 million sentences, right? And you give it this, you know, what's your concern? I give it the text in English, Japanese, and the text in English. Every time these pairs have to be correct, obviously, right? But then when you train the model, if it's a good model, then you would give it the Japanese text, the Japanese audio, and this should be pretty good. That's the idea. How did it do it? That's the magic of neural networks. That's the magic of transformers and generative. You know, how does ChatGPT do the things that it does? I mean, they know the architecture, but it learns these weights over massive training, right? Massive training. But yeah, that's one thing that it's like a new thing. Generative models are a new thing. And also this idea that sometimes you can just let the neural net figure it out. And then you start studying how did it do it, okay? But the key thing here is every S1 here, right? This is correlated to this one, right? And then the neural net, because think about what it does, right? Let's say that this is 2 and this is 70 and this is 135, right? I'm just going to use an example like that. And then over here, this one on the Japanese side. On the English side, this is 4, this is 350, this is 17, and a 1. Just that they're inconsistent, okay? Think of it this way. Given this one, you want that one, right? That's what you want. That's the reality of the world. When the model is first training, you give it this, it gives you random things. That's not good. But after a lot of training, you give it this, and it starts to give you a 4 over here. And then it gives you a 4 and a 1. And then surprisingly, the aha ChatGPT moment is when it gives you a 4, a 350, a 1, and a 17, and you're like, that's what, how did it do that? Do you see what I'm saying? And it's really because what it's learning is, now this vector is of size what? 20, I think I said, right? So size 20 vector, and this is a size 20 vector, right? Something like that. For 2 million examples, you gave it these pairs of 20 to 20, correct, right? And then you give it a vector of 20 with text and it's going to give you what? A vector of 20. And as I said, initially it might be pretty bad, but as it turns out, after a lot of training, that's where you start to get like really impressed because the things look pretty accurate. It might be that it gives you 4, 350, 1, and 15. And that 15 is not the 17, and yet it makes sense. You see that? One thing I found out when I was doing the English to Spanish is that it would translate the sentences shorter than the actual human, but not incorrect, just shorter. So I can show you, there's a paper that we wrote on that, and you can see what was it? Unexpectedness of it. The unexpectedness of it was interesting. Yeah, please.
So about coding the vocabulary with the numbers.
Yes.
Do you have to follow? Well, I'm sure the numbers will probably just normalize or standardize. So 49,000.
The numbers actually there's more to it. I kind of didn't go all the way. You don't leave the numbers as integers.
Oh, I see.
Yeah, you represent the numbers as vectors themselves.
Really?
You know what I'm saying? So like it won't be 70. That 70 now becomes a vector of, let's say, size 128. And that one, and all words will be a vector of size 128 that has meaning as well.
Right.
And that's what gives it the power. So if you ever heard of word to vec or something like that, that's the additional step. Yeah.
Another thing is, well, I guess then it probably will answer my second question.
Yeah.
Because one, how you pick the sequence down 50,000, do they, like, for example, you say 15 and 17, they're close in terms of numbers. Are they close in terms of
yeah, actually, like if it's 17 or 3 or 5, it's probably the on, or, and if it's like 44,500, it's xylophone or some other weird word. It's the frequency, yes. So all the algorithms because it's like 2 algorithms. You first run the vocabulary algorithm, and then you run like the actual neural network algorithm. So the first vocabulary algorithm is it takes all the text and looks at the frequency of the words, and then it looks at the most important ones. So there's tick token, which is one of the algorithms. BPE is another one. And these actually break words into, like I said, into syllables. Because happy, happier, happiest, happiness, you can actually construct that by saying hap and then adding the piece that goes after.
Like the roots,
Yeah. Yep. Got it? All right, so just to wrap up this one then, because this board is like covered in things. So let's go just wrap it up, right? So we are trying to convert. So what would be the answer here? Again, X and Y, right? You don't need to get lost because it's always, this is the key thing. It's always a correlation of inputs to outputs, where you almost let this, if you have a lot of data, you just let the machine learning algorithm figure it out on its own. When we start looking at CNNs and things like that, some of those ideas will start to make sense. All right, so then here, Remember, they're kind of similar in size, fixed in size. I'll draw this just to kind of remind you. We've got the audio part and the text part. We said basically 10 and 10, I think, or something. I didn't take it the additional step of taking every idea and representing it as a embedded vector, but that's key to it. Let's just say 20, 2 million. A sample is basically a sentence in English and a sentence in Japanese, a pair of them. And then the model will learn to correlate them. And eventually, one good way of thinking about it is, given a vector of size 20, it will give you a vector of size 20. And hopefully it'll have the thing that you, well, if it's a good model, it'll have what you want. I mean, you can make one that generates random, so there will be words in there. You just want, that's what optimization just gives you better, more accurate. Any questions on this one, guys? You get the basic idea of how to approach different problems like these. Okay?
So
Yeah.
Technically,
Yeah.
the bottom, the vector 20 should be horizontal, right? Like
Oh yeah. I just did it like that because it looks.
so
Because
just-
when you draw neural nets, we always draw them like
yeah,
this,
yeah, sorry.
and so that's kind of why I did.
Yeah, I see. But to to correspond to the,
Yeah,
Yeah.
it would be the rows. So this is sample 1, row 1 on one side and on the others.
Yeah.
The X and the Y. Yep. Got it? All right, great. So that should be the last problem of these word problems. Okay, so I'm gonna stop the recording.